และในลำดับถัดไปครับก็จะเข้าสู่ช่วงสำคัญอีกช่วงหนึ่งของกิจกรรมในวันนี้นะครับจะเข้าสู่ในส่วนของ knowledge sharing session นะครับโดยหัวข้อแรกที่เราจะได้รับการฟังการบรรยายในวันนี้นะครับเป็นหัวข้อ lesson learned in translating basic science to industrial implementation for carbon capture solvents นะครับซึ่งในหัวข้อนี้นั้นเราได้รับเกียรติจากวิทยากรต่างประเทศนะครับโดยท่านนะครับจะเข้าร่วมเข้าบรรยายในวันนี้นะครับผ่านระบบออนไลน์นะครับ so it is now my great pleasure to introduce Professor George Shimizu from Department of Chemistry, University of Calgary, Canada. Ladies and gentlemen, please join me to welcome Professor George Shimizu. Professor George, the stage is yours. Hello, are you hearing me all right? Professor George. Hello, Professor George. Can you hear me all right? Hello, Professor George. Professor Shimizu.
Hi, George. Can you hear us all right?
I can hear you. I can't really hear when anyone else is speaking.
Oh, it's okay. Then I'll be yours. All right. I think we're ready for you.
All right, I should begin.
Yes, please. Yes.
Okay. Thank you. Thank you to the Thai Nano Institute for the chance to speak to you and share some of our work on carbon capture. And I know it's only 30 minutes, so I will go quickly. And so today I just wanted to talk a little bit about some of the basic science of a solid that's useful for capturing carbon dioxide, but also just in terms of developing a project, what makes a good technical partner, and also managing intellectual property and being able to develop teams to help accelerate these technologies, as it's quite a long road. So when we think of carbon dioxide capture, there's actually many different things this can actually be. This is a review from now 14 years ago, and so this list has only gotten bigger, but I would say broadly carbon capture for me, you can break it down in one sense, is it by a liquid or a solid? And also whether it's a chemical bond or just a physical bond. So physisorption, chemisorption, liquid, solid. Between those four terms, we would encompass really everything here. And also there's membranes. So one of the things here is zeolites and MOFs under the adsorption category. So adsorption is just using a solid and having the gases condense. And MOFs are metal organic frameworks, and that is what I'll talk about. So in terms of just a picture of how a solid can act to adsorb carbon dioxide, really we are making things that just look like powder. But if you actually zoom in to the nanometer scale, you will see that there are holes about a nanometer in size. In our case, the compound I'll be talking about is less than 1 nanometer. But really, this is the kind of thing we're talking about. It's not just gas adsorption on the surface of particles. It's actually inside the holes, and that makes these act like they're molecular sieves. So what is a metal organic framework? It's the type of structure shown on the previous slide, but where you have metal components and organic units joining them. This is a contrast to something like a zeolite, where it's metal and then oxide is the linker. So in terms of changing these structures, you can change the metal to many different types of metal. You can change the linker, and by changing the linker, you change the size and the shape of the hole. Maybe what is more subtle is every time you change the shape of the hole, because we are talking about a hole that is on the size of a few molecules, not a huge hole. Changing the size or shape of the hole changes the way the molecules themselves interact inside the hole. And that is actually something very significant. For this class of compounds, I think they had always been regarded as perhaps not stable enough or too expensive to make in a very big scale. And I will show one example that shows that's not really the case. So how do we move forward? We have all of the projects in my research group begin by making about less than 1 gram of just a powder. So then how does that translate into interfacing with industrial carbon capture? I think what's very important is to at least be able to speak the same language. And this is something more and more appreciated now, that process considerations, rather than just making broad extrapolations from the molecular features. So in this figure from a very nice review by Marco Tadai and Camille Petit, I'm working down here. However, the person with the greenhouse gas problem understands this language, CapEx, OpEx, productivity. And so really the challenge is doing these experiments in the middle in a meaningful way and devising a process that makes the best use of this compound to tie the powder to the industrial emission. So the compound I'll talk about is one called CAF20. This stands for Calgary Framework 20. We published this almost 3 years ago now in Science, but now many other people are working with this compound. And I think I'm very happy to say everyone finds the compound is stable and has the same CO2 properties that we reported. For almost 2 years now, this compound has been part of a 1 ton CO2 per day capture pilot at a cement plant in Vancouver. And for about 1 year, it has been part of a 25 ton per day CO2 capture from natural gas combustion at a Chevron facility in California. And just at the end of last year, this won a prize for outstanding project for Canada at the Mission Innovation. This was announced at COP28. What is CAF20 then? So when this figure that I'm showing here, this isn't a drawing or a cartoon. This is actually a figure made from the actual X-ray data analysis of crystals of this compound. So this is really representing where the atoms are, and this is the exact structure. And this hole here is about 1/2 of a nanometer in size. And I won't spend a lot of time on the technical parts of this compound, but I will say why it's very special. This is a compound that absorbs carbon dioxide simply by the gas sitting and interacting with the walls. And so the gas is really just condensing in the hole. Now, because of that, it's very easy to release because it isn't chemically bonded to the structure. The challenge with this type of compound, though, it's a physical absorption. And so you would expect water to condense much more easily than carbon dioxide. And so I just want to emphasize this figure on the right. This is a plot of loading inside the hole versus humidity. And so the red here is carbon dioxide. And what we see is that the carbon dioxide is not affected by humidity up to about 35%. And even up to about 60%, it's over a millimole per gram, which is actually quite good. But the fact this is just a physical absorption and it's working in water at all is really quite surprising. This is the water uptake in the compound. And I think the most interesting curve here is the blue one. The blue curve is the water uptake in the presence of carbon dioxide. So not only does the carbon dioxide adsorb in the presence of water, with carbon dioxide, water is actually suppressed. Okay? And as there's only a handful of compounds that I'm aware of where this phenomenon is demonstrated, and they all have pores that are very, very small. But the other compounds that show this phenomenon, I don't believe they're very stable. Ultimately, you would need lots and lots of the compound. So in our lab, we were making this in buckets initially, and we could make a few kilograms at a time. Now, BASF, the chemical company in Germany, makes 2.5 ton batches of our compound. So as far as the demonstrations that are running, the technology is something developed by a Canadian company called Svante, and this is named after Svante Arrhenius, who first proposed the greenhouse gas theory. But Svante has two technologies that they do very well. One is how they take the powder and they coat it on sheets and stack the sheets with spacers, silica spacers, to make something that is very efficient for high volumes of gas to pass through. So that is inside this wheel. And so when the flue gas comes through this wheel, the carbon dioxide is trapped in the moth. So this is how the moth is formed. And the scrubbed gas passes through. The wheel then turns, and the regeneration is done with a rapid treatment with steam. So low-grade steam will pass through and remove the CO2, and then the CO2, the water is condensed, and the CO2 goes off for sequestration. Then, so the bed then is wet, so the bed is dried with hot air, and then it's cooled, and this wheel turns once per minute. Okay. Now, as far as why CAF20 works very well with their system, as far as first, it has to capture the CO2, and so CAF20 does have very good capacity and selectivity for CO2, but it's also very stable to the acid gases that can be in the combustion stream, as well as the water. When we go to release this, it's treatment with steam. So of course it has to be stable to steam, but HOA here is the heat of adsorption, meaning the affinity of the CO2 for the whole. Despite having a good capacity, it actually has a fairly modest binding energy because it isn't chemically bonded. When the CO2 is removed and then the solid is filled with water, you then have to remove the water. So you'd actually like the water to be quite easy to remove. And then this then needs to be stable to large amounts of air and oxygen that are going through. And then finally, everything has to be fast and it has to be very durable. The thing with using a solid is you can't really add more solid as it's running if the solid degrades. So this should run for a few years, ideally, without any maintenance. And an important thing I'll point out just in terms of assessing the material, all these things that I'm highlighting in blue are all very important, but they don't have anything to do with the carbon dioxide capacity or the isotherm. Okay, I think a lot of papers in this area seem to regard this as the most important thing, and it's just one factor. Right, so now as far as moving on to a process, I think maybe an obvious point for this audience is that, every CO2 stream is actually its own challenge. Natural gas is only 4% carbon dioxide. At a cement plant, you'd be closer to 20%. Hydrogen, blue hydrogen plant, 15 to 45% CO2. Steel plant, also 20%. So each of these would have their own unique solution. And by that, I mean it could be the same powder, but the engineering cycle would need to be optimized to match each of these streams, and not just in terms of the CO2 concentration, but in terms of the temperature, the pressure, all the process conditions, the flow rates, and also consider what is the available cheap energy at the particular location, even if there's another process running next to it that has waste heat that can be used. All of this should be factored in to optimize. When I say each process, it has its own optimal considerations. Usually, if these are representing two different compounds, and this is the carbon dioxide uptake, I think most people would say, well, of course, this compound must be better. It takes up so much more CO2. But depending on how you're regenerating the solid, if you're raising temperature or applying a vacuum, if this was more of a diagonal curve, even with the lower uptake, it would be better for changing pressure. Okay, so a very important point then is to assess materials under the process conditions that are suitable for them and not for other materials. There's often a tendency to say monoethanolamine captures at 25 degrees and is regenerated at 110 degrees. So we should compare everything to that. And especially if you're building an entirely new process, that's a wrong way to think about it. So as far as this whole project, how did we advance, and what partners were involved? So the very first stage is just developing the powder and doing some of the basic engineering tests, so benchtop scale work. And for our project, all of that was funded by one provincial agency and two federal government agencies. But these were all grants in the hundreds of thousands of dollars. I think in total, these grants might have totaled about $600,000 or $700,000. As far as the small scale process being done, the first level was a 0.1 ton per day capture. And the development of this was funded at Svante by the US Department of Energy, but also their investors. I think by the time they were doing some of our work here, they had already fundraised close to $100 million with investors. As far as doing the scale up of the actual powder, we had a startup company that was funded by the university and government funding. Svante also did some of the scale up at their location, but then ultimately they used some of their investor money to give a contract to BASF. So these are the different partners that were involved. Now we have the 1 and the 30 ton per day carbon capture demonstrations. And again, this is funded by Svante and their investors, but also the partners. So Lafarge for the cement company and Chevron, the oil company, are the hosts for the two demonstrations. As far as our management of the intellectual property, so CAF 20 was licensed to Svante, but I've always wanted the material to be capturing as much carbon dioxide as it can. And there are so many different opportunities to do carbon dioxide, whether it's biogas, but also different air biogas, different manifestations as well. And so right now we actually have 2 other licenses executed for this. One of them is actually not related to carbon dioxide, and we're negotiating two other licenses. And one of those is a student-run startup that I'll talk about in a second. But I think a very important point here, and this would be more for the people that are developing a very, very basic technology at the low technology level, that the development path here is very dynamic, and we have focused on genuine tech development rather than bird in the hand payouts. And what I mean by that, I think I could probably have have granted 3 other licenses to CAF 20 if I wanted to. But the partners they did not have an understanding of what was needed to develop CAF 20. They might say, oh, well, we're going to use CAF 20 to capture carbon dioxide from the air at shopping malls. And if you ask them, well, what will you do with the carbon dioxide once it's captured at the shopping mall? And they wouldn't have any plan for this. And then I would tell them, I don't believe CAF 20 would actually work to capture carbon dioxide from air. And then they would still want a license. And then I understand then that they want the license just so they can say, we have a famous compound we're using to capture carbon dioxide, please give us money. But there will never be any meaningful development. And that's really what I try to avoid. We want to give licenses to people who will actually be able to implement it for real carbon capture. And if we're giving it to everyone, it just makes it very, very difficult for the people who can really do something meaningful. So with that, I just wanted to show a very quick video. This is a new company we are engaging with, and very sensibly, they're starting with some very small scale testing of the CAF 20 to try to align with a natural gas turbine. And so this is only 2 minutes, but I think if you've never seen a natural gas turbine steam generator, this would be interesting. And this video is from, and they have funding this company from the carbon tax of Alberta, from the industrial carbon tax. And part of the funding, with that funding, they have looked at more than 60 different carbon capture technologies. And ours is one of the ones they want to do advance to a pilot. But with that funding, they also have an expectation of doing some public education. And so they have an open house at their facility for high school children. And that's what you're going to see in this video. Well, the video is not playing for some reason. Are you able to hear the sound?
Hey, did anybody prep you about the magically wondrous machine that I get to go show off? Do you know what it is? It is a jet engine in a building, literally. We're going to go watch an operating jet engine, right? That when he says it's loud, he's not kidding, right? Imagine standing next to a 747 with his engine pinned to the max. It's kind of loud, right? But it's kind of exciting. I can't wait to tell you all about that. One of these machines breathes 2.5 million kilograms of atmosphere a day. So imagine if you have 2.5 million kilograms of mass going in the front end at 20 degrees Celsius, you burn some gas in there and the temperature goes up. You get your 7.5 megawatts of electricity coming out the other side. You've got 500 degrees Celsius, 2.5 million kilograms a day worth of mass flow. If we were to stick some pipes filled with water in them, we can make steam out of that. This machine makes 1,300 tons a day. We use that to make 2,700 barrels a day worth of oil. But what else comes out of this thing? We get CO2.
Canada as a whole put out 670 million tons of CO2 equivalent in 2021. And of that, oil and gas is one of the larger contributors. We're aware of that, which is why we're wanting to do something about it. One of the things that we're going to work on here at the site, what we'll take is the exhaust from that jet engine, so a source. We'll capture it from there in a very large industrial process. We'll concentrate it and compress it so that we can transport it to an underground reservoir. It happens that the reservoir here is really safe and secure. There's a number of other layers on top of the reservoir that we'll be injecting it into, so it will stay underground.
We have designed a very simple experiment here today where we'll be essentially capturing the carbon dioxide which is coming out of your lungs. In this tube here, this is the metal organic framework. It's essentially just like a sponge which only pulls out carbon dioxide. So if you breathe through this, everything except for carbon dioxide will go through. In this one, just to make sure there's no trickery going on, it's just filled with glass beads. These solutions are basic. Once it becomes neutral, so if we add enough acid, like the carbon dioxide from our breath, it'll go to a yellow color. So what we can see is this one, right? It's turning yellow much quicker because it's not capturing the carbon dioxide. So this one's turned yellow. This is going to need a few more breaths because the compound is constantly pulling out the CO2. Thank you for our demonstrations. Great job.
Yeah, so that it's a very simple demonstration, but something I wanted to emphasize is that I remember I said this is a physical adsorbent, and that was typical human breath only has about 4% CO2, and it's certainly wet. And so the CO2 capture is working in a wet, fairly dilute stream. Okay, so as far as this project then, again, the basic sorbent design and engineering, go back to the laser pointer. This was provincial and federal government funding. It's the same sorbent. So in this case, the process and the small pilot development, this is from a grant from this industry, this particular company. They have a grant from the provincial carbon tax, and a provincial research agency will leverage that. And in this case, the solid scale up, we have to go to a different company because, well, for contract reasons, we're actually going to make a new startup to provide the sorbent for this. And we actually have a commitment for sales from the other licensee. So this is where the funding for that will come. And as far as the next scale, bigger development, it will likely be something involving this partnership with the carbon tax. Okay. I mentioned there was another startup company that was going to be involved with this technology. Another very interesting CO2 stream that is wet is fermentation processes. So making beer. So CO2 is actually the 5th ingredient in beer. And so my student, Nick, has created a startup called Turn CO2, and he has a demonstration planned at a brewery. And the nice thing about capturing at a brewery is when the CO2 is captured, you don't need a pipeline to take it to a sequestration site because the CO2 is actually needed to carbonate the beer. So the CO2 can go right back into the process. Okay. So just some final thoughts on this then. Some of the things that we have learned. I think when I was first making these compounds, I thought, well, who would help me? Who is my customer? And I thought it would be the person here. And it's not. Ultimately, they might be. But what I really need is the engineering partner, because this person needs the system. They don't need the powder. And so the entire chain is important. So taking the powder, making the proper form of the powder, and then having this be synergized with this engineering form. Okay. And so the person doing this can feed into many different types of industrial emissions. But I think the biggest challenge is this gap right here. Because I've asked people at this scale, what is the scale of a meaningful demonstration? And they will say, if it isn't 10,000 tons capture per year, it's not worth building. Meanwhile, over here, we're trying to get to kilogram scales. So in here, there are about 3 or 4 steps at different sizes, and they all need different partners and different levels of funding. And that's really an important point to de-risk. For anyone who might be in the room who's making the powder, you don't want to get too excited just because somebody wants to give you money. An investor who does not understand the development path, this is not helpful, right? If someone gives you $100,000 for research and thinks you're going to make them a millionaire in 1 year, this is actually a horrible partner in this space. Okay. So with that, I am finished. These are the numerous agencies that have funded this project. And I always like to end with a pretty picture. We're in Calgary, which is near the Rocky Mountains. And so this is a glacier. This is ice from the last ice age. And this is about a 3-hour drive from Calgary. So if you are in Alberta, please come visit. Okay. Thank you very much.
ขอเสียงปรบมือให้ Professor ชิมิสึนะครับเดี๋ยวจะมีทางดร.ปองการนะครับจะช่วย communicate เดี๋ยวเราจะมีประมาณ 1-2 คำถามในการที่จะสอบถามนะครับแต่ว่าผมขออนุญาต brief นิดนึงนะครับจากที่ได้ฟังนะครับ Professor ชิมิสึเราได้เห็นว่าทางแคนาดาโดยทีมของทาง Professor เองเนี่ยครับได้มีการพัฒนาในส่วนของ Carb 20นะครับซึ่งเป็นส่วนของการที่นำมาใช้ในส่วนของ Carbon Capture เราได้เห็นตั้งแต่มุมของการวิจัยว่าดูว่าตัววัสดุตัวนี้นะครับโดยปกติเนี่ยม็อบบางตัวเนี่ยจะมีการแข่งขันระหว่างตัวของน้ำแล้วก็คาร์บอนไดออกไซด์แต่ตัวที่เขาพัฒนาขึ้นมานั้นนะครับสามารถที่จะจัดการกับจับ CO2 ได้ดีมากๆนั่นคือเหตุผลหนึ่งที่เขาพัฒนาต่อครับจากผลแลบที่ดีมากๆทำในส่วนของการ up scale เพื่อให้สามารถผลิตได้เป็นหลักกิโลกรัมนะครับหลังจากนั้นเขาไลเซนส์ต่อในวิธีการไลเซนส์เนี่ยเขาเลือกไม่ได้ใครมาขอไลเซนส์แล้วเขาจะให้นะครับเขาจะเลือกเฉพาะคนที่สามารถไลเซนส์แล้วนำเทคโนโลยีของเขาไปใช้ได้จริงๆนะครับซึ่งก็ถือเป็นหนึ่งในวิธีการที่น่าสนใจมากๆเลยนะครับแล้วก็นอกจากนี้นะครับการต่อยอดในส่วนของด้าน engineering เราเจอวัสดุที่น่าสนใจแล้วแต่ระบบในการ capture อาจจะยังไม่เวิร์กดังนั้น engineering จึงเข้ามาก็มีการออกแบบในส่วนของ part engineering เพื่อให้สามารถใช้ในการ capture CO2 แล้วสิ่งหนึ่งที่ทาง professor ได้พูดแล้วน่าสนใจมากๆเลยก็คือซอสต่างๆของการปล่อยแก๊สคาร์บอนไดออกไซด์ในแต่ละแหล่งจะมีความเข้มข้นไม่เท่ากันดังนั้นส่วนนี้จะเป็นส่วนที่ challenge นั่นคือสาเหตุที่เราจำเป็นจะต้องมีการวิจัยพัฒนาทั้งในส่วนของวัสดุและก็ระบบให้สอดคล้องกับแหล่งปลดปล่อยแต่ละส่วนนะครับแล้วก็มีการพูดถึงในส่วนของtech transfer ที่น่าสนใจนะครับว่าของเขาเองเนี่ยมีมุมของการที่พัฒนาออกไปเป็นในส่วนของสตาร์ทอัพเพิ่มเติมนะครับก็เป็นแคปเจอร์แล้วก็มีในมุมของการที่ทำเบียร์นะครับดังนั้นอาจจะเราเริ่มเห็นแล้วครับว่าในแคนาดาเองเริ่มมีบทบาทในส่วนนี้เกิดขึ้นมากมายก็น่าจะเป็นอินสปิเรชันที่ดีที่ทางเราสามารถใช้เป็นอินพุตต่อได้นะครับแล้วก็มุมหนึ่งในมุมของด้าน policy ที่น่าสนใจมากๆคือการนำตัวของ carbon tax ต่างๆไปใช้เป็น funding เพื่อให้เกิดการลงทุนทางด้านนี้จริงๆนะครับก็น่าจะมีทอล์กแรกนะครับน่าสนใจมากๆคือเป็นการดึงตั้งแต่ fundamental จนถึงการเปิดเป็นบริษัทแล้วก็ใช้ได้จริงครับเอาละครับณตอนนี้นะครับมีสัก 1-2 คำถามจากในที่ประชุมนะครับเชิญเลยครับมีไหมครับเชิญเลยครับขอไมโครโฟนด้านนู้นนิดนึงครับสามารถถามคำถามทั้งเป็นภาษาไทยหรือภาษาอังกฤษก็ได้ครับไมโครโฟนไปด้านหลังนะคะ
Hello, Dr. Shimizu, right? I would like to know about the energy efficiency or energy economics of this method of carbon capture. Is it better than 60%?
ขอบคุณมากครับเดี๋ยวทางทีมงานกำลังประสานคำถามไปยัง
Question
Professor
from the
Shimizu
floor is to comment about the energy efficiency of this material compared to amine capture.
Yeah, okay. So the energy efficiency is very dependent on the specific gas stream. You can say the heat of absorption in CAF 20 is 39 kilojoules per mole. In the Svante process, a big part of the energy efficiency as well is what waste steam is available to do the regeneration. But they are very confident that for cement capture, that the cost can come down as low as $50 US per ton of captured CO2.
Thank you so much for the wonderful talk, George. Yeah, I think that's it from the floor. It's great pleasure to have you as speaker today.
Thank you very much.